In this video, we're going to describe how to write down a number called the equilibrium constant, which describes how the equilibrium is favored either toward the reactants or the products. And so it's a real simple mechanical thing to do. So if you have the reaction H2 plus I2 going to 2HI, then the way you write the equilibrium constant is you put the products on top and you use the square bracket to denote the concentration in molar. Technically it's not a concentration, but we're going to pretend it's the same. And then if there's a stoichiometric coefficient, you write that as a power, then divided by the reactants to their stoichiometric coefficients. So H2 to the first power, of course anything to the first power we usually just don't write the first power, and then I2 also to the first power. And so the equilibrium constant is written as, it depends on the balanced chemical equation. It does not depend on how the reaction occurs. So this could be a 100-step reaction with 100 individual steps, but if they're all in equilibrium, then there will be a ratio of the concentrations that obeys a certain number. Okay, so for example, if Kc for this guy is at a certain temperature, okay, you can measure the concentrations of Hi and I2 and I2 in molar. It might be 340. Okay, so that number is larger than 1, which means the numerator is larger than the denominator. And if the numerator is a larger factor than the denominator, then that means in some sense there's more product than there is reactant. So any K larger than 1, we call it product favored. In this example, let's write down the equilibrium constant. Again, NO squared divided by N2 and O2. This is the reaction that occurs in your automobile engine and creates NO that comes out the exhaust pipe that hopefully the catalytic converter can convert back to nitrogen and oxygen. Okay, and it turns out that at a particular temperature, for example, this might be 2 times 10 to the minus 9. Now this number is much smaller than 1, which means the numerator is much smaller than the denominator. And if you have a large denominator, you have a lot of reactant, which means in some sense there's not much product. Okay, so the smaller the K, the less product you expect. The larger the K, the more product you expect. And of course this continuous range. There are some extremely high Ks, some extremely small Ks. And there are some Ks that are very close to 1, and in that case you have a mixture of reactants and products that are all similar magnitude. Okay, and then finally, look at this example. This is slightly different. Oops, SO3 squared, and then SO2 squared, and O2 to the first power, which of course we don't write to the first power. But anyhow, it's a very simple thing. So this to this squared, this squared, this to the first. Next thing we're going to do is ask ourselves a question, and we're going to do that with the first equation here. We're going to ask, given some concentrations, can we find the final one? I'll be right back. So the question we're going to work is, if the hydrogen iodide is 1.52 molar, and we know that these two are equal to each other, we should be able to solve for the molarities of H2 and I2. So simple, you just substitute into an algebraic equation. So you put in the number for Kc, which is 340. You put in the number for Hi, which is 1.52, squared. And then in the denominator is our unknown value. We'll call it x. We don't know this and we don't know that, but it's basically x times x. So a little algebra gives us x squared equals 1.52 squared divided by 340. Now before we do this, let's look and see, do we expect HI to be a larger number or a smaller number? Okay, so 340 says we expect more product, and so we expect the reactants to be less than 1.52. That's a guess. There are some unusual situations where it might not be true, but that's what we're expecting. Okay, so let's just go ahead and solve this equation. I'm going to get a number here. And it's x squared equals 0.0068. And then x is the square root of that, 0.0824 molar, right? That's what we expect. All right, so 0.0824 molar, 0.0824 molar, 1.52 molar. All right, so the last thing to do, and it's important if you have the time, is to actually check that this number is correct, okay? So what you do is you calculate the actual numerical value of K with the numbers, the whole set of numbers now. All right, so you'd write the expression and then literally put in all these numbers. You say 1.52 squared divided by 0.0824 squared, and it should be 340. Okay, so let's do that. Okay, let me try that again. $340.3, which is basically that 0.3 is just round off error. So the 340 is correct at 3 digits.